Hello and welcome back to more examples of graphing in our calculus course. I've got two more functions to graph out for you a little more carefully. Again, these are functions that we encountered in videos back from sections 3 and 4 from earlier this chapter, and we're just going to try to finish it up. So our next function is y equals sine x plus cosine x, and we're only going to graph this on the interval from 0 to 2 pi. And so again, sine and cosine are defined everywhere, and so our domain is going to be the entire interval from 0 to 2 pi. We don't have to worry about anything there. And we don't have to worry about behavior as x goes to plus or minus infinity either, but we do need to talk about intercepts. And so our y-intercept comes from plugging in 0. I get sine 0 plus cosine 0, and that's equal to 0 plus 1 or 1. So I've got a y-intercept of 0, 1. And then for x-intercepts, we're going to solve sine x plus cosine x equals 0. That's sine x equals minus cosine x. And we kind of saw something akin to this back in section 4.4 when we were looking at, turns out, points of inflection. But we want to remember that sine and cosine have opposite signs in quadrants 2 and 4. And they have equal magnitude at the odd multiples of pi over 4. And so that means that in this case, x is going to be 3 pi over 4 and 7 pi over 4. Those are the angles in quadrants 2 and 4 where the sine and cosine have equal magnitude. And then in this previously part here, I've got all the information about increasing, decreasing behavior, relative max, relative min, local max, local min. I'll call them by the names that we are using in this text. Relative is a synonym for local. And then we have 2 inflection points, and those are going to be turns out to be at the intercepts. So let me draw my lines here again. And this time we're only going between 0 and 2 pi. So the way I've got this marked off, every unit down here is pi over 4. So every horizontal unit equals pi over 4. And so I'm going to be increasing from 0 to pi over 4. So I'm increasing here. And then from 5 pi over 4, and in between, I'm decreasing. So again, this is pi over 4, pi over 2, 3 pi over 4, 5 pi over 4, 3 pi over 2, and 7 pi over 4. And then for concave up, concave down behavior, I've got dividers at 3 pi over 4 and 7 pi over 4. And I know that I'm going to be concave down here, concave up here, and concave down here. So I can plot a few points. I know that I'm going to start at 0, 1, and I'm going to have intercepts at 3 pi over 4 and 7 pi over 4. And I've got maximums at square root of 2 and minus square root of 2. We want to remember the square root of 2 is approximately 1.414. And so I'm going to be about here for my local max. And then at 5 pi over 4, at about the square root of 2, this is going to be my local min. And now here I go. I'm increasing and concave down, and then I'm decreasing and concave down, decreasing and concave up, increasing and concave up. Sorry, And then finally increasing and concave down, and I'm going to wind up being back here at 1. And so again, notice how I'm using these combinations to draw the graphs on the appropriate intervals. Finally, we're going to look at the function that we've spent some time with in the recent past, y equals 16x over x squared plus 4. So if I want to think about domain, again, this is going to be all real numbers. And that's because x squared plus 4 is always greater than 0. So I don't have anything to worry about 0 in the domain here. In terms of intercepts, my y-intercept, once again, this doesn't happen all the time, but it's happened frequently in these examples. Y of 0 is equal to 0 over 4, which is equal to 0. So the origin is my y-intercept. And then for the x-intercepts, I'm going to set 16x over x squared plus 4 equal to 0. Well, a fraction is equal to 0 when its numerator is equal to 0. And so this is my only x-intercept as well, the origin. So it's both an x-intercept and a y-intercept. And then I want to look at limit as x goes to infinity of this expression. I could do this a couple of ways, but I'll remind us about L'Hopital's rule. This is an infinity over infinity form. So if I use L'Hopital's rule, I'm going to get 16 over 2x. I've got 16 over a big number. And so this is going to be going to 0. So y equals 0 is a horizontal asymptote. And I get the same thing if I look at the limit as x goes to minus infinity of this function. Still an infinity over infinity form. And so I get 16 over 2x. So while it was a big positive number in the previous case, it's 16 over a big negative number, but that's still heading towards 0. But notice that it is coming at 0 from below, because the y-coordinate is negative, and this is going to be approaching from above. Okay, so again, this is all information that I constructed earlier about increasing, decreasing, local max, local min, etc. And so let's sketch in our horizontal lines here, and we'll try to set this up for increasing, decreasing, concave up, concave down behavior. The places where it changed increasing, decreasing behavior were at plus and minus 2, and we went decreasing, increasing, decreasing, and then square root of 12 was approximately 3.5, and so for our concave up, concave down behavior, I've got changes right about here and at 0, and then right about here. And we start off concave down, and then we alternated back and forth between concave down and concave up. Now I want to plot my intercept and my local max and local min. So I've got an intercept right here at the origin, I've got a local max at 4 when x is equal to 2. So I'm going to have a local max right here, and then at -2, -4, I've got a local min. And then inflection points were at minus square root of 2 of minus square root of 12 and positive square root of 12, positive square root of 12. And so that's going to be, roughly speaking, right about here. So about -3.5 and then -3.5. So here is an inflection point at -√12, -√12. And I've got one up here at +√12, +√12. So I've got my anchor points down, and now I want to remember that I've got a horizontal asymptote of y equals 0 on both sides. But let's start off here. So I'm going to be starting off concave down and decreasing. So it's going to be doing something like this. And then it becomes decreasing but concave up. It's going to connect to here. Maybe I can do that a little better. And then it's concave up and increasing. Ugh. Sorry. Concave up and increasing. Then it's increasing and concave down. Like that. Concave down and decreasing. And then decreasing and concave up. And it's going to head toward this horizontal asymptote here of y equals 0, and I get the same thing over on this side. And so this is a reasonably careful graph. I can maybe tidy this up just a little bit to show the maximum better. And so I've got this graph. And so you'll want to be modeling these sorts of things on the assignment that I've got before you.